Let's look at some of the basic concepts in static timing analysis. The main objectives of this module are where does static timing analysis fit into your flow, and also identify timing library information for timing arcs such as uniqueness, cell delays, net delays, and slew. When you design a circuit, you need to make sure that it's working correctly. There are multiple ways of doing that. You can run a functional simulation, but that is only checking to see if your circuit will actually function correctly. You can run a spice analysis, but that takes too long for each path because you have to time millions of paths. So in static timing analysis, we look at the circuit devoid of any time frames, and so simply just add the cell delays and the net delays from the libraries or elsewhere, come up with the path delays, and then we just compare these path delays to a timing specification as given by your constraints. Synthesis tools convert your RTL to gates. Place and route further optimizes your design. In order for these optimization tools to find the right cells for the right location, they rely on static timing analysis to calculate the path delays. Static timing analysis has to time millions of paths every hour to give the correct information and accurate information to these optimization tools so that they can create a circuit that meets your timing requirements. Finally, the same static timing analysis is also used to analyze the timing of the circuit to make sure that your circuit works at the required frequency, but this is done using many more requirements and more stringent requirements like sign-off requirements. Each of these tools, which are considered sign-off tools, have different flavors of or ways of doing their timing sign-off and different capabilities. So this is a typical flow for your design. First, we specify circuit functionality and timing libraries. You'll then capture your RTL and write constraints. And if we provide all this input to the synthesis tool will then convert this RTL to gates using the libraries, and while doing that, the synthesis tool will try to meet the timing constraints. So this is the first time after we use the synthesis tool. The synthesis tool is using SDA internally to figure out what cells to use. And then later on, at the end of synthesis, we run static timing analysis to verify the timing of the synthesis results. And when we are satisfied with that, we push it to place and route. And in place and route, we again use static timing analysis to place the cells and route the design in such a way that it meets the timing requirements. And the SDA is used for this purpose to meet timing. And then finally, we run the final verification using sign-off tools to verify your design if it meets your timing requirements. And then once we're satisfied, we push the design to layout. The timing engines that are built in synthesis and place and route software provide for a very fast way of selecting cells for synthesis and place and route so that the synthesis and place and route software can optimize the paths for better timing. They all have this function of providing the timing information to these tools. You also have the timing verification tools which provide for the final sign-off after design is synthesized or placed and routed. So these timing verification tools typically sign off on all the different timing checks and all the constraints, whether the design is meeting the specifications or not. The timing tools in synthesis, or the timing engines in synthesis and place and route, they often try to calibrate themselves to make sure that they correlate well with the timing verification tools. Timing libraries provide delays of cells, interconnects, or also known as nets and wires. And apart from this, they also provide power information and slew information and such. So the STA tool uses this information to calculate the path delays and then verify these path delays against the constraint requirements that are provided. So the standard format that is widely used in the industry is the Liberty format, or also known as .lib. And there are other formats like ECSM or LBR that are used by different tools internally, but most of the tools do accept the Liberty format or the .lib as an input. So as we've seen before, the STA tool is calculating the timing path delays. These timing paths mainly consist of two basic elements. One is the timing arc in the cells and the timing arcs of the nets. So basically the goal in timing is to restrict the path delay to a certain amount as specified by the constraints. So in this example we have a flop, and this flop provides timing check data. So the checks are also part of static timing analysis. So what are timing arcs? If a change on the input is causing a change on the output, then we have a causal relationship. So if the input in this inverter is rising and the output is falling, or when the input is falling, the output is rising. So this dependency of the output on these inputs basically is called a causal relationship, and each of these imaginary arcs between the input and the output is called a timing arc. So it's important to understand timing arcs so that you can determine the path delays correctly. Because not every arc is symmetric. So the rising to falling arc is probably not the same as falling to rising arc. So we need to determine each arc based on how the input is actually behaving based on the inputs. All of this information is provided in the timing library, and we'll try to understand each of these relationships and the purpose of each of these timing arcs and the information that is provided in the timing library. So the following characteristics, unateness, slew, and delay, are all different characteristics of a timing arc. Each of this information can be obtained from the timing libraries. So let's look at what each of these mean and what their purpose is. Unateness is a very important property of all timing arcs. Static timing analysis uses unateness extensively to determine how the timing information is calculated. So if we look at the example of a buffer, the output is rising when the input is rising, the output is falling when the input is falling. So basically, the timing arc is positive unate because the transition of the output is the same as the transition on the input. If you look at the inverter, when the input is rising, the output is falling, and when the input is falling, the output is rising. So basically, the transition is the opposite of the input transition. So therefore, this is considered as negative unate. Some arcs, of course, can be non-unate, where there is no relationship between how the output is changing against the input. But most of the time, you can easily determine the uniqueness of a timing arc by looking at the truth table of that particular cell. So for a buffer, you can actually say, oh yeah, it's going from 0 to 1, and the output is changing from 0 to 1 at the same time. So that kind of gives you clues into how to determine the uniqueness of each individual timing arc. In certain cells, there are multiple inputs, so we have to look at each timing arc to determine what the uniqueness of that particular timing arc is. So for every input to output relationship, that is one arc.
In this picture, you can actually see the timing sense of the different arcs of a cell. So the timing sense of a NAND gate is shown as positive unit, and the other one is shown as negative unit. Every input to output combination forms a timing arc. Each related pin under the timing section of the output pin represents a timing arc. Uniqueness of a timing arc is specified in the library by the timing sense attribute. When the net B is rising, net Y is falling. Therefore, the timing arc is negative unit. When net A is rising, net Y is rising. Therefore, the timing arc is positive unit. Try the following activities to reinforce your learning. Transition time is the time that a signal takes to change states from low to high or high to low. The picture or the graphic shows the signal rising from low to high and signal falling from high to low. These rise and fall transition times are the properties of a timing arc. Usually, rise time and fall time are measured between 10 and 90% or 20 and 80% of your input signal or your output signal and calculated as rise times or fall times. Technically, the rate of transition is measured in volts per nanosecond, and it's called a slew. And transition times, such as rise and fall times, are measured in terms of time, typically nanoseconds. So the slew is the rate of transition, and STA tools measure input transition time and output transition time using slew thresholds. These slew thresholds are defined in the library, and the input rise and fall times are calculated from the slew thresholds. STA tools use the slew threshold values to calculate the transition times. So here's an example that we picked from the .lib. The STA tools calculate the rise time from slew lower threshold percentage rise of 10% and slew upper threshold percentage rise of 90%. So similarly, STA tools use the fall threshold values for fall time. So in this graph, we see that the fall slew is calculated from 80% to 20% of the falling signal, and the rise slew is calculated from 20% to 80%. So the thresholds of signal calculation time are used to calculate slew. Slews are typically measured in a small percentage voltage range, like 40 to 60, to capture a more linear portion of the transition. These measured slew are then scaled to the library slew thresholds. So from the .lib, we have an example here where slew is measured to be 0.05 at the range 40 to 60, so it's a 20% swing, and the library slew thresholds are 10 to 90, which is an 80% swing. So this slew is basically recorded as 0.05 times 80 by 20, which is 0.20.
Timing libraries capture everything in the form of table lookup, and also known as lookup tables or LUTs. And the example shown below is actually nothing but a representation of what's in the library in the form of a table, and is more easily readable. So if you want to identify what the output transition is, just picture the table actually plotted as index 1 and index 2, and slew is index 1, load is index 2, and you basically look up in the values what the value is for that corresponding slew and corresponding load. So identify what is index 1 first, identify what is index 2 first, and then just find your value based on the lookup table. So for output transition, this is the example that is shown that is plotted between output load and input transition. And so based on the example for an input transition of 0.05 and the value of output load 0.021, based on the lookup, the value is shown to be 0.293559. It would make it easier if you can remember that index 1 is always the row and index 2 is always the column. So that way you can always identify what the values are based on the index 1 that is specified and the index 2 that is specified. Because delays of the next stage depend on the slew of the previous stage or the input transition of the previous stage, we calculate the next stage transition and slews based on the previous stage using these lookup tables. And basically what we do is the STA tools calculate the output transition times and slews from the library and use that value as the input transition to the next cell in the same path or next stage. So this is how we propagate the delays and the cells and find out the delays throughout the path from these lookup tables of one stage to the next and so on. Because the input signal is constant and the signal is actually traveling across many stages along the path, the slew at the output of one stage degrades before it gets to the next stage and so on and so forth. And so especially as it travels along a long net, you'll see slew degradation happen. Same thing through a cell, you'll see slew degradation happen. So as the slew degrades, the signal actually degrades as well, and basically the delays get longer and longer based on the slews degrading. And so we need to capture all these slew degradation as we go along, and there is a lookup table for slew degradation as well, which uses the output pin transition and the interconnect delay or the net delay and calculates the degradation, and you'll see these degradation tables in there in your timing libraries. These kind of calculations actually kind of give you the overall timing through that path, how bad it would degrade based on these slew degradation tables.
Try the following activities to reinforce your learning.
Depending on the process technology, different physical elements have different levels of contribution. Each stage delay, whether it's cell delay or net delay, represents the time required to propagate a signal from the input of one stage to the input of the next. Delays encountered in digital circuitry are composed of two main components, cell delay and net delay. However, with process technologies above 90 nanometers, cell delay has been the major limiting factor in time enclosure. However, At process technologies below 90 nanometers, net delays dominate the cell delays.